Now the identity, okay, the identity is if there exists some element such that my IVTs over N1, N2, and NP gives me, and when it is composed with any other IVTs, then the original result remains. The components do not change. Then that's the identity element of the integral value transformation, because of which the components do not change themselves. Now we come to another operation, modular addition and multiplication. This is for cellular automata if mu I 1 and mu I2 are two local configurations, then addition modulo P over mu1 and mu2 is equal to mu1C Ci and addition modulo P mu2 Ci. Individual components addition will be done. Individual cell we will have the modulo addition and the modulo multiplication operations. Similarly for IVTs also, individual components we will add or multiply accordingly for modular addition and modular multiplication, and we will add and take the modulus of it to get the result. So this is the modular multiplication. We will multiply and take the modular value. Now for cellular automata, if we consider, previously we considered composition of mappings. Now the function we are considering as modulo addition and modulo multiplication. So then what are the results that we get? Then we see that that the set of all transition functions form a commutative ring with identity. Earlier with composition of mappings, we had normally got that with to be forming a group. Now this we have proceeded further with modulo addition and modulo multiplication. It forms a commutative ring with identity. Already with modular addition, so the extra ones we need to see is for the identity element and the inverse element, because these are all being functions, closure and associativity normally follows. Now the identity will be such that my transition function gives all 0 elements. That will be the identity function. And multiplication in multiplicative identity is the such a function that my states go to 1. So these two exist. So naturally, the set of transition functions form a ring. Okay, and we have to see the inverse also. So clearly, for any state Bs, there exists some other state B inverse for such that modulo addition has an inverse, and modulo multiplication also there is an inverse existing, and commutativity and distributivity follows from modular addition and multiplication laws. Hence we have this theorem for transition functions. Let us see what happens for integral value transformations. Now this forms a commutative ring under modulo addition and multiplication. So here we don't get the identity element for multiplication. Addition identity element naturally occurs, but not the multiplication. In general, let us see. Where it gets stuck is closed in associativity follows. Additive identity is also obtainable because we can get some sequence of functions such that we get 0 function, but it is not always that we can get a sequence of function which gives me 1. So that is why we don't get multiplicative identity. And commutativity follows. Commutativity and distributivity over modular addition and multiplication normally follows. But when we take some restriction over the set of integral value transformations, that the set of natural number is restricted to the states set Q, then it becomes almost identical with the transition functions of CA, and then naturally identity occurs. What we had the problem was previously here no, the definition of IVT is such it is a sequence of functions.
5 minutes, please. Within 5 minutes,
Yes, sir.
please. Okay.
Yes, sir. It's a sequence of functions, fj of this one. So many functions are there. So their multiplicative identity stops. But however, if we restrict it to state Q, then we have only one function over here. It can this IVT is represented by just fj and the individual components eta 1, eta 2, eta k. So there it is possible to find in multiplicative identity such that we get one, and so such a function obviously exists. And so this integral value transformations, when restricted to state set Q, follows a commutative ring with identity. So that was the theorem. So these were all our results. So what all we did was we have seen the relation how IVT can be represented, how used to represent Wolfram code, and then the domain of IVTs if restricted from positive integers to p-based numbers, which gives us the state set. Then an odd dimensional IVT can be equivalently treated as a local transition function of a CA. And all transition functions of CA forms commutative ring with identity. However, IVTs in general, we can get up to commutative ring under modular addition and multiplication. But when restricted to p-based numbers, then we can get a commutative ring with identity because multiplicative identity exists. So we had such some references. Thank you.
So, any question from audience, please? If there is no question, again I repeat, I invite questions.
Hello, Sreeya. Actually, I want to
Yes.
ask one question. Uh,
Yes.
okay, can any CA be represented by IVT, or only some CAs like
Yes.
linear CAs
No,
can be
no.
represented by that?
No, any CA can be represented by IVTs. That
Because
is
you
one.
have shown one example of rule 150, that is linear CA, and
Yes.
there the XOR T that was shown, so it was a linear CA.
Yes.
So how other CAs can be represented, because these were the simple XOR operations that were shown there.
Okay. So that is a special IVT I mentioned. Let me get back. Okay, you were mentioning about this. So this rule
Yes, yes.
150 is a linear CA that can be represented by exclusive or transformations. Exclusive or transformations are a subset of integral value transformations. Any integral value, any Wolfram code. See, this is a generalized rule 69800. This is a generalized Wolfram code, not even elementary CA. So we can represent this also by an IVT. So any CA can be represented by an IVT. We can increase the base, we can increase the dimension And we can have leverage over IVTs. Over CA impact representation becomes easier. Some special linear CA or one or two CAs fall under special IVTs. So we under integral value transformation, we have specialized integral value transformations like modified carry value transformation and so on. Those are restricted, yes, but the IVT in general is anything can be represented by an IVT.
So for the cellular automata, you need to know the total rule and the local functions. Then only you can represent it to IVT, right? Right. That
Yes,
is
for cellular automata, yes. Actually, IVT has a bigger domain. So, cellular automata is one of the domain which can be represented by an IVT.
because if you increase the dimension or the number of neighborhood or the number of states, then you will get many number of local transition functions. And then you
Yes,
need to know all the transition functions and then only you can transform it to IVT.
yes, but that from see like analogous logic to Boolean logic, you can form right. In these numbers are basically we are naming it to be cellular automata rules, but these are basically p-based numbers. For an IVT, we treat it as a p-based number. You can take this suppose 69800. You change it to a two-based number. This will be such and then you can apply IVT rules. You need not know cellular automata for IVT, but cellular automata rules can be represented as as an application of IVT.
Okay. Thank you,
I
Shreya.
mean, I can treat any natural number. For that matter,
Okay.
for IVT is dependent on any natural number. So that can be any base, any dimension.
Okay. Thank you, Shreya.
I may put one question to Sreeya, that if anybody asks, is there any superior points on behalf of IBT against cellular? What would be your answer?
Yes. So what this one, what I was saying, we have an ease of representation of for an IVT. I mean, for CA, we have to think about neighborhoods and all because Wolfram code might we can represent it definitely for CA, but it is difficult to implement the Wolfram codes because of the robustness. I mean, it becomes big if I number of states become big, then it will become big. So number of functions will increase. It's going to be difficult to handle. But for an IVT, it's just a natural number which we are dealing, a p-based natural number. So it's easier to deal. Computation becomes easier. That's one advantage.
Okay. Thank you, Sreeya. So, if
Yes.
there is no other question, I must move to next speaker.
Okay. So
Our
I'll
next
stop
speaker
sharing.